sampling distributions.
The Seattle Epidemiology Research and Information Center, in collaboration with the Department of Veterans Affairs, the VA Employee Education System, and the University of Washington Department of Epidemiology, present the 2002 VA Epidemiology Summer Session.
Okay, welcome back to General Biostatistics. The topic we'll now be looking at is common statistical tests that are used in comparing proportions of two groups. So in the last lecture we were looking at comparing means of two groups. Now we'll look at comparing proportions. So remember that when we compared means we had a continuous outcome of interest. Now what we're interested in are groups that have a dichotomous outcome of interest. So these are data that we typically can see displayed in a 2x2 table. We're going to review some methods for summarizing information in 2x2 tables. We're going to look at how to test for differences in proportions between two groups using the Chi-Squared Statistic, and we'll see that there's an underlying methodology for this, but also a shortcut formula for a 2x2 table Chi-Squared Statistic. So, as I said, the outcome of interest is now a dichotomous one. We're looking at the proportion of individuals that have the disease or an event of interest, an outcome of interest that can be expressed as success or failure, diseased or non-diseased, response, non-response. Question that I have received is, why would we sometimes be interested in looking at proportions rather than always looking at differences in means? So for instance, suppose we were interested in response between two groups. We might actually have more information if we compared the differences in mean response times between groups. But sometimes we might not have the actual times. We might just have the information on whether by a certain point in time, say 6 months, there had been a response or non-response. So what we have is a situation in which we're interested in whether two groups are the same with respect to some dichotomous outcome. We can look at displaying this information in a 2x2 contingency table. So here, suppose I use the example of having two treatment groups, A and B. So here we have 50 observations in treatment group A, and we have 70 observations in treatment group B. So think of these as 50 patients treated by treatment A and 70 treated by treatment B. And suppose that by 6 months we were looking to see whether they responded to treatment, yes or no. So what we have then are the totals. The total number of responses was 54. Non-responses was 66, totaling the 120, which equaled the 50 patients treated by treatment A and 70 treated by treatment B. Now, if we were interested in whether they differed with respect to response, we could look at and calculate the proportion responding under treatment A and treatment B. So the proportion responding takes the total who responded in treatment A, 37 divided by 50, which is 74%, or a proportion of 0.74, whereas in treatment group B, 17 out of 70, or 0.24, responded. Does there appear to be a difference in response between the two treatment groups? Yes, and in fact it appears that there's a much higher response in treatment A than in treatment B. The question is this difference in response likely to be one that we'd get just due to chance alone if there was truly no difference in response rate between the two treatments? So we can calculate proportion responding in both treatments. What's the overall proportion responding? 54 divided by 120, which is 0.45, or 45%. So how could we summarize this information? We just talked about using 74% as a percentage responding in A and 24% responding in B. There are other ways that sometimes can summarize this information. We could say based on this there's a 50% absolute difference in response rate between treatment A and B. where there's a higher response in A. We could look at the relative difference in response rate compared to one of the treatments. And so here I could look at the difference between A and B relative to B. So if I took that difference of 0.5, divided it by the response rate in treatment B of 0.24, I would see that I would get a ratio of 2.08. And if I multiplied by 100, that would say that the proportional increase in response rate was 208% higher in A relative to B. So you may see it reported as an absolute difference, a relative or proportional difference. You might even see it given by the odds of responding. So what's the definition of odds? The definition of odds is it's the probability of responding divided by the probability of not responding. So in treatment A, the probability of responding was 37 out of 50. What was the probability of not responding? 13 out of 50. Let me take you back to the table. So 37 out of 50 responded, 13 out of 50 did not respond. And by definition, we could consider the odds to be 2.85. So the odds of response in treatment group A is 2.85. Similarly, we could look at the odds of response in treatment B by taking the probability of responding, which was 17 out of 70, divided by the probability of not responding, and we would get 0.32. A common summary might be the odds ratio of response. So it compares the odds in treatment A to the odds in treatment B. So we would take 2.85 divided by 0.32, and we would say that the odds of responding are 9 times higher in A than in B. So all of these are just different ways of summarizing the same information. What would you conclude regarding any of these? Regarding response rates in the two treatments? A seems to be better in terms of response rate than B. So in this statistical comparison that we're interested in making, we're looking at the question, is the difference in the response rate that we observed bigger or larger than what we would expect due to chance alone if there was truly no difference between the two treatments? So let me take you through reasoning how you might, how we use the Chi-Squared statistic to calculate this. So here's that same 2x2 table, but we're missing the inner cells. So what we know is there were 50 people treated by treatment A, 70 by B, and that the overall response, number of responses was 54, and 66 did not respond. Okay, so I just have the marginal totals of this table. Well, by reasoning through this, what frequencies would we expect if the response rate was the same by treatment? What would you expect? Say that again, please. So you'd expect 54 divided by 120, which is 45%? Is that what you said? Yeah. So if we looked at just the total who responded, which is 54 divided by 120, remember that was 45%. So if the response rate was the same in both treatment groups, wouldn't you expect 45% of the 50 people treated by treatment A to respond? And wouldn't you expect 45% of the 70 treated by treatment B to respond? Yes. So let's fill out the rest of the table. So 45% of 50 is 22.5. 45% of 70 is 31.5. These are the numbers we would have expected. Now you're going to tell me that we can't have half of a person responding, but this is just for the purposes of looking at expected counts. And how would we fill in the number that don't respond? Right, subtract from the total. So 50 minus 22.5 gives the remainder, the number we'd expect not to respond. 70 minus 31.5 gives the number we'd expect to not respond in treatment B. And so here they are just filled in. So now this is a table. These are the expected frequencies of response and non-response, if there was truly no difference, how does that compare to what we observed? That's the next table. So can anybody tell me what they observed? Here's a comparison. This is what we observed in our treatment groups. Here's what we'd expect if there was truly no difference in response rate. How do these two tables compare? They're much different. So what we see is that there appears to be a higher number who respond in treatment A than what we'd expect, right? And a lesser number who don't respond in treatment A. Now, compared to what we expect, there's a lesser number who don't respond in treatment B. So what the Chi-Square statistic does is it makes a comparison of the observed to the expected counts. So we could eyeball this and we say they look much different. We'd calculate the Chi-Square test statistic to make a formal comparison of observed to expected counts, and we would do this for all 4 cells of this table. So the Chi-Square statistic is one that looks at a comparison of observed and expected. It squares it because some of those comparisons might be negative, some might be positive. So we're looking at a squared difference divided by expected. Now, suppose that what we observed in our data was what we would have expected. Then what would this numerator look like? 0. So if what we observed was exactly what we expected, the observed and expected counts were the same, this numerator would just be equal to 0. What would the value of the Chi-Square statistic be? 0. If what we observe is quite different than what we'd expect, what happens to the numerator? It increases. So as the difference between observed and expected increases, the value of the Chi-Square statistic becomes larger and larger. So we're going to use that as a test then. By calculating the test statistic, we can use this as a test of independence, or another way of saying this is that we can test that there's no association between response and treatment. Another way of saying it is that the two groups, the two treatment groups, are the same or homogeneous with respect to treatment response. So we can use this test statistic, which follows a Chi-Square distribution. It's another distribution. It's not bell-shaped like the normal or the T, but it is a distribution that depends on the degrees of freedom. So how would we calculate the test statistic based on this data? What we saw was the observed counts that are always given in the first place, the expected counts that we had from that 2x2 table. These were expected based on what? Right, this was based on expecting 45% to respond in both treatment groups. In other words, that there was no difference in response rate in the treatment groups. So if we look at observed minus expected squared divided by expected, total these for all 4 cells, we end up getting a chi-square of 29.1 with 1 degree of freedom. Is that close to 0? No. Not close to 0. Is it likely that we would have observed these differences just due to chance alone? Well, we don't know yet until we look at the appropriate chi-square distribution and the probability associated with it based on its appropriate degrees of freedom. So for our course, all that we're going to worry about is a chi-square with 1 degree of freedom. So I don't have it listed here, but it's in the chi-square table at the back of the textbook. When we have a 2x2 table, the degrees of freedom are always the number of rows minus 1 times the number of columns minus 1. How many rows do we have? 2. How many columns? 2. Rows minus 1 is 1. Columns minus 1 is 1. Degrees of freedom is 1. And the only value with a chi-square with 1 degree of freedom that we have to worry about is that the probability or significance level of 0.05 is associated with a chi-squared statistic with 1 degree of freedom equal to 3.84. So how does 29.1 compare to 3.84? Much higher, indicating that the p-value is going to be something much less than 0.05. Does that make sense? What's the whole point of this chi-square statistic? It's just looking at how much discrepancy there is between observed and expected. How much discrepancy there is between 37 and 22.5, between 13 and 27.5, between 17 and 31.5, etc. And it's reflected then in this chi-square statistic of 29.1, which is very large. If there was little disagreement between observed and expected, this chi-square statistic would take on values closer to 0. So again, reiterating, if what you observe is what you expect, the numerator would be equal to 0. This chi-square statistic would be low or equal to 0. Okay, so this was the long way of calculating the chi-square statistic. There's a shortcut for 2x2 tables that takes, you don't have to calculate expected counts at all. All that you have to do is label the cells as A, B, C, and D. Then we can talk about the row totals. We can talk about the column totals. And the shortcut formula says take the overall total of 120 and then multiply it by the cross product of A times D minus B times C. So in your notes, make sure that says C. A times D minus B times C squared divided by the product of the row and column totals. So just taking the row totals, the column totals of 54 times 66 times 50 times 70. So that's on the next slide, which shows we take the overall total and then just take A times D minus B times C, that quantity squared, divided by the product of the column times the row totals, and we'd come up with the same chi-square statistic of 29.1. All that it is a shortcut if you're doing it by hand. Now, I can show you this in Stata as well. And what were the 4 cells, A, B, C, and D? 37. B was 13. Then I'm going to indicate I'm going on to the next row with a backslash, 17 and 53. So using the tab I command, it'll give me the 2x2. I'm going to put a comma there and indicate that I would like the chi-square statistic, and I'd also like it to show me some row percentages. So I'd made a mistake. Thank you. Okay, so now here's that 2x2 table that you have in the notes. So what is this showing? It says drug A, drug B, 74%, meaning 37 of 50 responded. 17 out of 70, or 24%, responded in B. And what we see is the chi-square statistic of 29.1 that basically has a p-value that's very close to 0. Very close to 0. Now, some of you have said, well, this is one way, the chi-square test is one way. There is another way to do a z-test with proportions. And the z-test with proportions is just as we had a difference in means with 2 groups, we can look at a difference of proportions with 2 groups. And in Stata, we would use something that's called proportion test, PR test, again, immediate. So I'll tell it that I had 50 in treatment A, and the response proportion was 0.74. And then there were how many in treatment B? 70, remember, with a response of 0.24. So now, here's a 2-sample test of proportions. We get a z-test, a z, which is 5.4. What's the p-value? Same thing that we got when we looked at the chi-square. In fact, there's an algebraic relationship that if we squared this z of 5.4, we would get that chi-squared value of 29. that we calculated by hand. It's just an algebraic relationship. The bottom line is that our interpretation is the same, whether we calculated the chi-square test or a z-test that was looking at the difference in these two proportions. So we will not go into the other methods outside of the chi-square test for looking at difference in proportions, but what if I looked at the 95% confidence intervals for each of these proportions? They're calculated in the same way, based on this proportion of 0.74 and placing an interval around it. So we see the first group, treatment A, ranges from about 0.6 up to 0.86. The confidence interval for treatment B ranges from about 0.13 up to 0.34. Similar or different? Very different. Well, I don't think they overlap. They go from 61.8% to 86.1% for treatment A. The 95% confidence interval for treatment B goes from about 13.9% up to 34%. They're very distinct. So this would also tell us that there appears to be a very statistically significant difference in the proportion of response between the two groups. So I wanted you just to be able to see that although we're emphasizing the chi-squared as one way of easily looking at a test of whether two proportions are different between two groups, there are other methods we could do, like we just did, a z-test of the difference in proportions. When the cell counts are small, something known as Fisher's exact test could be used. We also illustrated that we could look at the separate confidence intervals for A and B, but we could also look at the confidence interval for the true difference in proportions between the two groups. And then these can be expanded to looking at odds ratios and confidence intervals, or even ways of combining information from multiple tables. But these are all advanced topics that we won't be looking at today or ever. So we'll be focusing just on the chi-square as a simple test of the differences in proportions. So I hope that this made some sense. If we looked at testing differences between two proportions, we're really asking, are the groups the same with respect to some outcome or characteristic? Another way of phrasing that is by asking the question, is there an association between group and characteristic? In other words, between treatment group and response. Another way of phrasing that is asking, are group, treatment group, and response independent? But we would use a chi-square statistic to answer the question however it's phrased. There is a question.
The degree of freedom you had in the last chi-square, again, go over how you calculate it.
Right. So for our purposes, when we have two groups and we're comparing proportions, the degrees of freedom are always 1. But the way we would do this for any contingency table that has R rows and C columns is that the degrees of freedom is the number of rows minus 1 times the number of columns minus 1. That's the general formulation for degrees of freedom. Let's see, another question?
Is the use of the chi-square statistic valid when you have more than two groups?
Yes. So if you have 3 groups, and we will be talking about that tomorrow, if you had 3 groups and you were interested in knowing is the percent responding in treatment group A, B, and C all the same, we could use a chi-square statistic that would have 3 rows and 2 columns. So we'll be covering that as well in the next lecture. Let's review last night's homework. Remember that our topic yesterday was looking at setting the framework for statistical inference by looking at sampling distributions. Remember that sampling distributions are theoretical distributions, but we can think of it as the probability distribution that describes the values that different sample statistics may take. And under certain assumptions, the values that that sample statistic may take will be approximately normally distributed, centered at a mean. So we can think of this as the mean of the statistic with a standard deviation which reflects the variability or spread in the statistic. It's this sigma, the sigma that's associated with the values of the statistic, that's referred to as the standard error. So two of the most common sampling distributions that we focused on were the sampling distribution of the sample mean x bar. So if we place this into context, we can think of, in theory, if we sampled from a population that had a true mean mu and a standard deviation sigma, and if we could compute all the possible sample means from all possible samples of size little n and plot them on a histogram, the shape of that histogram would be approximately normally distributed. The mean of the sample means would be the same as the population mean mu, and the spread, or the standard deviation of the sample means, would depend on the standard deviation in the population, sigma, as well as the sample size. So the spread in the sample means is sigma over the square root of n. And similarly, if we had a dichotomous outcome, the theoretical sampling distribution of all possible sample statistics has a mean that's equal to the true population proportion and a spread that's equal to the square root of the true population proportion p times 1 minus that, or q, divided by the sample size n. So the reason we spent some time on this is that these sampling distributions underlie the basis for statistical inference, both in terms of estimation as well as hypothesis testing. So keep in mind that with estimation, for a confidence interval estimate, we're taking the sample statistic that we observed based on our single data set, forming an interval around it by adding and subtracting an appropriate z or t tabled value, depending on the alpha of interest, times the standard error that corresponds to that theoretical sampling distribution of the sample statistic at hand. And in general, for hypothesis testing, the test statistic that we use in a hypothesis test is formed by taking the value of our observed sample statistic from our data minus a hypothesized value divided by the standard error of the sample statistic. So we're using the spread in the sample statistic, or the standard error, both in forming the confidence interval as well as in setting up the test statistic for the hypothesis test. So let's use this theoretical framework then and look at a few examples from the book. One example is one in which you're given hypertension prevalence estimates based on the N. Haynes survey conducted from 1976 to 1980. And we're looking at differences here in hypertension prevalence between whites and blacks. So the question at hand is there a difference in the prevalence of hypertension by race? So the fact that these are estimates means that based on our data, we have a dichotomous outcome. An individual either has hypertension or not based on a certain cutoff. So we have two estimates here. In the book, it's expressed as a percentage, 25.3% of whites and 38.6% of blacks. And the standard error that corresponds with it is also a percentage. 0.9% is the standard error. In other words, that's the variability in the sample statistic, the square root of p times q over n, of 0.9% in whites and 1.8% in blacks. Now, in order to work with these proportions, since these were expressed in percentages, all that we need to do is divide by 100. So we would see the sample proportion of whites is 0.253. The sample proportion of blacks with hypertension is 0.386. And the standard errors as well would need to be divided by 100 for a standard error of 0.009 in whites and 0.018 in blacks. So how could we construct confidence intervals for the true but unknown prevalence of hypertension in whites and in blacks? So for each group, we would take the sample proportion, form an interval around it by adding and subtracting 1.96, corresponding to an alpha of 0.05 for a 95% confidence interval, times the standard error that's based on the square root of p hat q hat over n. Now, keep in mind that what we were given in this example was just the standard error. So we were already given the square root of p hat q hat over n. Do we need the sample size? No, because we're already given the calculated standard error. So for whites, this confidence interval could be expressed as the sample proportion of 0.253 plus or minus 1.96 times the standard error of 0.009. And if we go through the math, what we see is that we have a 95% confidence interval ranging from 0.235 to 0.271. This is a confidence interval for the true population proportion. This allows me to say that I'm 95% confident that the true proportion of whites with hypertension in this time period is contained in this interval that ranges between 23.5% up to 27.1%. Similarly, for blacks, we could calculate the 95% confidence interval by taking the estimated proportion that we got of 0.386, adding and subtracting 1.96 times the standard error of 0.018, and again, going through the math, I would be able to say that I'm 95% confident that this interval that ranges from 35.1 up to 42.1% contains the true population prevalence of hypertension in blacks. So now how would we interpret these? They're both fairly narrow intervals. Is there a statistically significant difference in the proportion with hypertension in whites versus blacks? Yes, because we see fairly narrow confidence intervals that don't overlap. So by looking at this confidence interval, we see that there appears to be a higher prevalence of hypertension in blacks as opposed to the prevalence in whites. Now, just a few questions that we could also ask. These are 95% confidence intervals. What would happen if we were asked to construct 99% confidence intervals? The only change is that instead of using a z of 1.96, we would use a z of 2.57. We have now 99% confidence, but what happens to the width of these intervals? They increase. Whereas if we were looking for a 90% confidence interval, in other words, one in which we have less confidence, the z statistic would be 1.645, and we would have much narrower intervals. So again, remember these z's of 1.96, 2.57, and 1.64 just correspond to the areas in two tails of the normal distribution that we can find in the tabled values. Now, that example that we had looked at was looking at proportions, estimated proportions, and calculating confidence intervals for the truth and the populations, the broader populations of whites and blacks. Suppose that we look at this next example, which is dealing with a continuous measurement, that of body mass index, measured by taking weight in kilograms divided by height in meters squared. In this scenario, we are presented with a study of 58 middle-aged men who develop later in life diabetes. And we're told that in this sample of 58 men, the sample mean BMI was 25 kilograms per meter squared. The sample standard deviation was 2.7 kilograms per meter squared. And suppose that we were interested in constructing then a 95% confidence interval for the true mean BMI in the population of all middle-aged men who develop diabetes. We'd take the sample mean again, sample statistic of the sample mean, form an interval around it by adding and subtracting now a t times the standard error of the mean. We don't know the true population standard deviation of BMI. We get our best estimate by using the sample standard deviation, S. So the standard error is given by S over the square root of n. And because of our lack of knowledge of sigma, we would use a t, still with alpha of 0.05 split in two tails, but the degrees of freedom depend on the sample size, -1 or 57. So just to follow through on this, we would take the sample mean of 25 plus or minus the tabled value of 2 times the standard error of the mean that we get by taking 2.7 divided by the square root of 50 And our confidence interval ranges then from 24.3 kilograms per meter squared up to 25.7 kilograms per meter squared. What does this allow me to conclude? I can say I'm 95% confident that this interval contains the true population mean BMI for middle-aged men who develop diabetes. I can also say that values ranging from 24.3 up through 25.7 are consistent with the truth based on this sample of 58 middle-aged men.
Good day. My name's Gail Reiber. I'm the director of the VA Summer Epidemiology Program. Here in Seattle, I'm a VA career scientist and a professor at the University of Washington in health sciences and epidemiology. During the summer program, we've brought some very interesting faculty in to address topics of interest to our VA colleagues. I'm happy to welcome Dr. Mike Gaziano. Dr. Gaziano is the director of MAVERICK, the Massachusetts Veterans Epidemiology Research and Information Center. Dr. Gaziano is also a professor at Harvard University. He teaches grant writing at the School of Public Health. So I would like to ask Dr. Gaziano some questions that might be helpful to future researchers who are going to be writing grants. So if grant writing is in someone in the audience's future, what advice do you have in terms of getting started?
Well, there's a lot that has to happen before you even begin to write the grant. The first thing is you have to have a good idea. And good ideas can come from anywhere. It can come from your clinical practice. It can come from an RFA. It can come from prior research that you've done. The next step is to search the literature and make sure your idea is at least somewhat novel. And that should be followed by a discussion of what funding agencies might be receptive to your idea. These could include the VA, the NIH, private foundations, specialty societies, or even the university. It's essential to have a team assembled before you begin writing, and this could include a statistician, collaborators, budget analysts to help put your budget together, and then it's time to begin to write.
Okay. Grants seem to be fairly complex, and there are a lot of different portions of grants. What are actually the most important portions of grants, and how would one go about thinking through those portions?
Well, the grants are structured somewhat differently depending on the funding agency, and the first step is to understand the rules of the grant application for each agency. But most grants have four key components: a specific aims, a background and significance section, a section for previous work, and your methods section. The methods is the meat of the grant. The specific aims is designed to lay out your objectives and your hypotheses, and to give an inkling of how you're going to implement your aims. The background and significance defines the problem and identifies the gaps in knowledge that your study will answer, and alludes to how your study will fill in those gaps. The significance portion of this part of the grant tells why it's important to know that information. Is it something that is an essential piece of information to reduce morbidity or mortality or save dollars? The next section is previous work. The previous work section derives from work of others in the field or from your own preliminary work. It's a great place to put pilot information. And what the previous work section is designed to do is to give the reviewer of your grant an idea of the background behind your methods, the scientific method behind your methods, the scientific underpinnings of the elements of your methods that you're going to choose to implement your study. But the real meat of the grant application is the method section. And it has several components. I begin with an overview of the method section, telling the author what's going to be laid out in the method section. A simple paragraph defining your overall design is essential. The next steps in a method section depends a bit on your design. You usually define your study population, inclusion and exclusion criteria. You want to define the measures that you're going to employ to collect data, your baseline instruments, lab measurements that you might use, a plan to follow up the participants, If it's a observational study, you want to clearly define the exposures that you're interested in. If it's a trial, you're going to define the interventions. Fundamental to any method section is how you're going to deal with the data once you've collected it. So a careful analysis plan that's laid out with the help of a statistician is essential. Also, a statistician can help define the power that your study is going to have to answer the specific questions. And last, I think it's important to bring up issues about limitations in your grant, but don't bring up fatal limitations without having some way to address those problems. You should have an answer for the limitations that you raise.
Okay. The abstract seems to be pretty important to people on review panels. Describe the importance of the abstract from your perspective.
Yeah, the abstract is key. And I always write the abstract at the very end of the process. And it should summarize your aims, your study population, the problem, the gaps in the information, and then your basic approach. The reason an abstract is so important is because it sets the tone for the reviewer. There are many reviewers on a study section that will review the abstract, and because they're not the primary reviewer, the abstract will be a fundamental area where they're going to get a lot of information to be able to review your grant and to do a focus review. So the abstract is very important and should not be done in haste at the last minute.
Okay. You've mentioned that the people that review the grant are going to have a lot to say about things. Would you describe what's going to happen to this grant once it's submitted to an agency?
Well, typically, the grant first undergoes some sort of administrative review, where people who are not concerned about the science will see if you follow the rules. And grants can be rejected if you don't follow the rules. If you didn't follow the font size regulations or the number of pages in the grant, your grant can be sent back without a scientific review. If it makes that first hurdle, it gets passed on to a review panel, often called a study section, which is comprised of your peers. They're usually people who have some expertise in the particular field in which your grant falls. The study section will score the grant, and study sections from various agencies have slightly different strategies. Usually there's a numeric score. In addition, there is a careful critique of the grant that will be provided to the applicant. The scoring process allows that study section to rank all the grants that were reviewed at that particular point in time, to rank them from top to bottom. And often more important than the numeric score is the percentile score. The next step is those scores are passed back to the funding agency, because study sections are often independent of the funding agency. And it's up to the funding agency to decide whether there's enough funds to fund your grant. And typically, an NIH or VA study section will fund 20 to 30% of the applications in one given study section.
So if we don't do well the first go-around, what are our choices?
Well, there are several options. You could receive a fundable score, which means you have to get to work because you've made a commitment. A grant is a contractual arrangement with the funding agency, and if you ever want to get another grant from that agency, you better deliver on the promises made. Many grants don't get funded the first time, and what you have to do is do a careful review of what the problems in the grant were. So careful review of the critiques. You often will get the critiques before you get a funding score, or before you get a funding decision, and that'll give you a clue as to whether or not this will be a fundable grant. If it's not funded, it's often worth having a discussion with the funding agency to see if it's worth resubmitting. Many times it is. Most grants are not funded the first time around, and persistence does pay off. Sometimes your idea just wasn't ready for the study section. You have to educate the study section before they're willing to accept your idea as a viable path.
Sometimes when grants aren't funded and it's a new investigator just starting out, would you recommend broadening the portfolio and looking to different sources that maybe not be merit review right off the bat?
Yeah, I think it's a great idea to think about targeting it to the right level. There are many beginner grants. Private agencies like the American Heart Association or the NIH have startup grants that are small in scope, and you can take a small idea out of your main proposal and frame it as perhaps a pilot study or a beginning investigator award. You can also take a grant that wasn't funded by one agency and submit it in response to an RFA or to another agency that might have interest in your application.
So a young investigator just starting out shouldn't be discouraged by an initial negative result.
No. If we were discouraged by negative results, the senior investigators wouldn't be here either.
Okay. If you had to give one piece of advice to a new young investigator, what would that be?
Well, I think the key thing is to get organized. Putting together a grant is a major orchestration, and it involves a lot of work besides the sitting down and writing. And you have to have the big picture view. Keep your deadlines in mind and stay organized.
Thank you very much, Dr. Gaziano.
It's my pleasure.
Good day. My name's Gail Reiber. I'm an epidemiologist and health services researcher at the University of Washington and the director of the VA Summer Epidemiology program that's occurring here at the University of Washington. I am happy today to introduce to you some of the participants of the VA epidemiology session and share with you some important characteristics of the VA in general. I've asked Dr. Gordon Starkeybaum to join me today. Dr. Starkeybaum is the Director of Healthcare at the VA Puget Sound Healthcare System. He's a rheumatologist, he's a professor of medicine at the University of Washington, and he is also Associate Dean of Medicine at the University of Washington. Dr. Starkeybaum, you are affiliated with a very interesting healthcare organization. Would you tell us a little bit about the VA healthcare delivery system?
Thank you for inviting me, Gail. VA healthcare is a nationwide and complex undertaking. In the United States today, there are nearly 25 million veterans, and in that group, a subset seek care at VA hospitals and facilities all across the country. We last year saw nearly 4 million patients, both outpatient and inpatients. Those patients saw providers and visited nearly 42 million times across the country in facilities at 163 different medical hospitals, as well as over 800 clinics throughout the country. And the budget for the healthcare part of VA is almost $22 billion. There's 220,000 employees. So we're a very complex, large organization providing care to these veteran patients. One of the features, I think, that makes it so exciting, and one of the reasons I came to this class, is VA is trying very hard to systematize the care of patients and the population of patients that it cares for. We obviously take care of a variety of patients, but we also have a very robust data system, and we attempt to use that information to provide us information on how well we're doing and where we can improve care for these patients.
How is the healthcare system organized in the VA?
Right now there are 22 what are called networks, or Veterans Integrated Service Networks, or VISNs, which sounds curiously close to visions. And each one of those then has its own governance and facilities. For example, in our network in the Northwest, which covers a very large part of the landmass because we also include Alaska, we have Alaska, Washington, Oregon, and Idaho. We have 8 facilities and about 12, I think, outpatient clinics. And we try to integrate our care so that there is coordination and planning throughout this entire area. And that provides a major benefit to veterans who travel in and out, in and among those facilities. And it's particularly set up because the tertiary care needs are met primarily in the large urban centers, both Seattle and Portland VA medical centers. And so a patient, for example, at the Spokane VA Medical Center who needs cardiac surgery would be offered that surgery at the VA Puget Sound in Seattle.
In addition, are there other, don't a lot of your patients not only benefit from inpatient and outpatient care, but also nursing homes, home health, things like that?
Absolutely. And we really do have a very large encompassing medical care model, from outpatient clinics to inpatients to nursing homes to domiciliaries. So a patient who is enrolled with VA can, in a sense, have expected to have coordination of his entire spectrum of healthcare needs, from medications to hospitalization to outpatient services, radiation, surgery, and, if necessary, in some cases, nursing home.
Now, given that there are 25 million veterans and only 4 million are receiving care in the VA, why is it that such a small proportion actually are cared for by the VA?
Well, that's a good question, but resources are the short answer. We have, with $22 billion in the budget, we consider ourselves stretched in order to provide good care to those 4 million. And you should realize that we are focusing on a subpopulation of those patients, of those veterans, so that we're looking both at elements of service connection as well as their monetary needs. And Congress has, in a sense, made this through a series of priorities, and those are based on both consideration of service connection as well as income status. And I think what we do focus best on and most on are lower income and patients with disabilities and with special needs. And so that is something that has a much higher percentage of veteran patients captured under our healthcare system.
So how do you identify and best manage those high-risk patients in the VA system?
Well, that is, of course, a major challenge for us, because we do want to husband our resources properly. We want to provide adequate and optimum care. And so we need to pay attention to patients who have special needs and so on. I would say that, we're still learning about how best to do this. We use data. We have a computerized system in the VA that captures a number of parameters. We can use that information to approach sort of the high-risk patient. By that, we might mean a patient who is going to have, in the future, special needs and expensive needs. And so how can we manage, for example, a patient who may be heading towards a stroke? How can we anticipate that and put things into place to prevent them from having the stroke, so that they don't become such an expensive health burden for our system?
Would one of those strategies be clinical guidelines?
I think so. In other words, clinical guidelines reflect a compilation and recommendation by expert bodies of individuals, not simply in the VA, but some are modified in the VA, to say what makes best sense to provide care for these patients, and based on evidence and so on. And so using clinical practice guidelines is a tool and an approach that we think would be useful to manage patients.
Now, patients with many chronic disease present management challenges. How are you working with patients to address some of their educational needs and management challenges?
I think that's an excellent question. We know now that simply providing the doctors and the staff with a clinical practice guideline and saying, follow this guideline and take care of your patients in the clinic setting where you have 20 minutes and there are multiple problems to be addressed, is a major challenge for us. And so I think that we're coming to understand that we really do need the cooperation and the involvement of patients. After all, it's their medical problem, and they're the ones that should benefit from this. I think this concept and approach has been put out by the Institute of Medicine in their Crossing the Quality Chasm report, which very much endorses a patient-centered approach to care in this 21st century. And so the challenge in VA is how do we reach our patients? How do we educate them? How do we approach this issue because these are complex diseases, and there needs to be a great deal of thought and attention put into that.
I know that the VA has taken an initiative in looking at patient satisfaction. What kind of feedback are you getting?
Well, when we ask questions of our patients, by and large, they like the care that they get in VA. In other words, our satisfaction scores in many areas, in terms of courtesy, attention to their needs and so on, are very good. They don't like to wait, and so access is often a problem, both in the clinic or at the window in the pharmacy, or for seeing a specialist, or things of that sort. And so we're aware of some of those satisfaction issues and are trying to address those.
Congratulations on the good work that you're doing, and thank you for being with us today, Dr. Starkey-Baum.
Thank you.